Okay, welcome back. We're back for part 2 of our second method of our twins. We're just talking more about twin primes and some method to try to come up with a twin prime equivalence, or talk about how do you prove there's infinite twins. And for me, I just literally clicked and started a second video here. I just didn't want it to be much more than an hour, and we were already at an hour and 15 minutes. But it was a good stopping point, or a good point to just at the end of a section here to continue. So if you're just seeing this, go back and watch part 1 and you'll see where we're picking up from. And we were at the point where we're noticing there's something about... So we went through, we created our two surfaces. We're looking for values that don't ever appear on these two surfaces in a given column range of columns and rows. That's very important. So we're only checking certain values in certain columns and rows. Then we did some stuff to hone in and said, well, we can cut off the edges of those columns and rows and just use the lesser of the two pairs and the greater of the two pairs to cover our entire range. Even if we get a little redundancy or something, we want to check both domains, and we squeeze them into one. And then we're looking at that and we said, okay, we're honing in on values that don't exist. And we noticed that trailing values is what we called certain values at the bottom parts of certain columns. These trailing values won't appear in either chart. And because the one chart's bigger than the other, we said, hey, we're just honing in on what's happening with these trailing values in this second chart. And then it got a little convoluted at the end. If you're not familiar with it, you'll really have to go through with this stuff and familiarize yourself. But again, I'm just trying to paraphrase what the logic here is and do it quickly enough to kind of get people first access to this kind of thing. So we noticed that there was some little technicality that I wanted to point out at the end, that since we were kind of asking a general question now about every column, compared to, we kind of only want this question to be valid for columns where z was a prime and 4z then won't show up on these values. We know that there are an infinitely number of primes, so there will be infinite ranges and domains where we would end up with this last column and our value won't be there. But there's cases when, for what we're looking at, a value wouldn't have appeared in our little range that we're looking for. But if we don't know that that's going to be a prime column, if we want to call it that value would have appeared for some other z and invalidated what we were trying to do. And how can we get around that little part? And so that's where we left off. And we're going to use some parabolas and a bunch more of lines and scanning or other relationships here to find a value that meets that requirement, that gets us around this little part that we just noticed here at the end. So at this point, a range of 8 values is being checked, because we said the one surface is the other surface plus 8. And we're only checking those trailing values, and so it turns out that we're checking 8 values. Okay. Those values are checking each 4z, because again, we did our substitution where we made a substitution between 4z and s. And so when we're checking a number z to see if it's prime or composite, on our surfaces, we're looking for the value 4z. Okay. By returning the surfaces to be directly in returning the surfaces to be directly in terms of z. So okay, I'm going back from 4z to z here, I believe. And hold on, I got a cat coming up on the desk. Hi, kitty. That range of 8 shrinks to only 2 values. So because we made that substitution from z to 4z, or s to 4z, or everything about it, when we return the surfaces to just looking for z, that range of 8 is 8 divided by 4. There's only 2 values that we're checking that meet the requirement on a scaled down version of those surfaces. Substitute back in for s in equations in 14. And should I scroll back there just to see for what that was that we're looking at? So there's our equation 14. And you'll get this, and 15. because one was for one surface and one was for the other, you'll get that z equals minus y squared plus 2xy over 4, and that plus 8 over 4. These two surfaces have a difference of 2 as they represent the original prime and pair surfaces. Excuse me. When they evaluate to whole numbers, the difference of 2 lands on those whole numbers and therefore contains only one whole number value in between those two that does not show up on the surfaces in that range. When the surfaces evaluate to mixed number fourths, because they have a fourth here, so something, of fourths, the difference of 2 contains 2 whole number values in between those two that do not appear on the surfaces. This is shown plotted with y along the horizontal axis. So again, here I'm only saying that we're taking that trailing range of the surfaces that we were looking at and we're squeezing it down even more. And when we revert back to our original surfaces, that when these are whole numbers, you get one number in between them, and when they're fourths, you get 2 numbers in between them. So here's the whole number solutions. So here's a graph for the whole example for the whole number solutions, and x equals 6. So what are we showing here? We've got these two parabolas for a given x. So when you have a given x, this is a formula of y squared plus y over 4, which is a parabola. And same here. And so when these things evaluate to whole numbers, and what do I mean there's one value in between? Well, here's your two parabolas. Here's for x equals 6. And you'll see it hits a number, and there's one value, 10 in this case, in between. And when those parabolas are fourths, you'll see that there's 2 values in between the peaks of those parabolas. Okay, great. The value ranges being worked with were based on the diagonal squares when x equals y. That is what we were using for this trailing rule. So they're both either, what am I saying here? So they're both either even or odd in this instance. The value ranges being worked with were based on the diagonal squares when x equals y. And so they're both either even. So we're saying compared to that diagonal, which is what we were using, the value ranges that we're working with now. Whether x is even, then y is going to be even, and x is odd, y is going to be odd. From equation 18, one can show that when the values are both even, so now we're looking back at this. We're doing a little bit more simplification here with the forms that we have and thinking about our diagonal values and what happens with these. When it's multiples of 4, you get one number in between. When it's fourths, you get 2 numbers in between. But now we're saying from those, you can see that when the values are both even, then those numerators are multiple of 4, and thus the surfaces are whole numbers and you get one thing in between. The single value sandwiched between them then alternates between even and odd. Whenever that number is composite, it will appear in at least one later column and fail as a number not on the surfaces. This may not be immediately apparent as to why, and is discussed in a section at the end of the paper. Okay. Furthermore, if it were not the case, one could simply choose to only work with the mixed number fourth values anyways, as is done in the next paragraph, since it doesn't matter which source gives the generating values, so as long as an infinite number of them. Okay. I'm not going to muddy too here. I'm just going to go on and assume that you'd either have to figure this out or read what I said, or because this is a lot of just technical stuff, and it looks like I'm going to talk about it at the end anyway. But I'm obviously covering the cases that anyone who gets familiar with this would say, well, what about this or what about this? And I think I'm saying here again, you have to go verify this. But when you when the values are both even, you get this multiple 4, and then you're asking what the value is in between. Here it's 10, but you'll see that it goes even, whatever those values end up being, it goes even, odd, even, odd. Whenever that number is composite, the number that you get in that result, let's see, it will appear in one least later column and fail as a number not on the surfaces. Okay, This prompts us to restrict the search to only odd values of x. And more specifically, oh yeah, I'm kind of remembering what I did here now. Let's see. This prompts us to research only odd values of x, and more specifically, the odd value contained between the surfaces when they take values of mixed number fourths. This now narrows the search to only one recurring location on both charts, which will produce a value not on the surfaces for some range of columns. I think I'm later going to have to, I'm trying to jump ahead and remember what I did. I think if you're jumping ahead, you do understand or follow what's going on still. I think we end up saying that number has to also be prime. I can't remember if I had to do that or not, but we'll see here in a minute. But let's see, what am I doing here? I'm trying to just paraphrase it for you so we can get through this. To only odd values of x. More specifically, the odd value contained between the surfaces when they take values of mixed number fourths. This now narrows the search to only one recurring location on both charts. I'm just trying to read ahead to get my mind back around this again. Let's see. Since the value is coming from the surface where x equals y, I'm just thinking about this for a minute. So basically what I'm doing here is when the values are both even, you end up with this result. And we're just going to avoid that altogether. So we want them to be odd. But when they're odd, when they're even, you get this result when they're going to be multiples of 4. But when they're odd, you're not necessarily. So that's what we're using here. We're just avoiding all those even cases because we don't want it to have this thing that I describe here happen. So we're only looking for these odd values of x, and specifically want the ones contained between the surfaces when they take values of mixed number fourths, which I said there'll be two numbers. Oh, okay, that's right. So you could show that when they take when they're both odd, you get, and they end up with those values of fourths. I said that when they're even, you get one number in between, and it depends on whether that number itself is even or odd or whatever happens here. But when they're odd, you get two numbers between. But they're two consecutive numbers. So because they're two consecutive numbers, one of those will be even and one of those will be odd. So that's what I mean here. We're trying to restrict ourselves to that odd number. And again, I might have end up going further and end up saying that it has to also be prime. But we're going to restrict ourselves to that odd number in the case where we get two numbers, and it's the fourths. You can find this number by adding 3/4 to the surface with the lower values, or subtracting 5/4 from the greater. So here's the surface of the lower values. We add our 3/4. I could have started with the upper one and subtract 5/4. since the value is coming from the surface where y equals x, this simplifies the equation into a parabola for odd x. This is shown below as the new upward parabola selects the odd value between mixed number fourths for an odd x. Okay, so z equals x squared plus 3/4, x equals odd. And let's look at what I have here. So what I've done here is a missing number from both surfaces for a given range. So, okay, so here we've done where you can see, I'm going to zoom in for a minute. You can see on these two parabolas for our two surfaces, this is one of those cases that I was describing before where now the surfaces are fourths. And you can see their value here on like for x equals 5, the value is 8 1/4 and 6 1/4. But because they're fourths and where they end up going around two integers, which will always be consecutive, in this case 7 and 8, and that therefore one of those integers will be odd, and we want to hone in on that. And so that's what this whole section here is telling you how to do, and say, okay, you can use this parabola, this x squared plus whatever z we're working with. You're going to say z is equal to x squared plus 3/4 for some odd x. In this case, the example was 5. And this value here would be, so for example, in this case, x is 5. That gives you 25 plus 3 is 28/4 is 7. And you'll see that this parabola, this x squared plus 3/4, will select our odd value between our two parabolas. And that parabola here hits this odd value between 2, and you see it hits at 7. And that's our odd value between these two parabolas. Great. Therefore, for any odd x, x squared plus 3/4 will create a value that is not on either surface for a certain appropriate domain of parameters. Which we haven't fully addressed that part yet. Because there's infinite odd numbers, the parabola x squared plus 3/4 generates infinite such values. Okay. It's important to remember that there are many other locations among the surfaces where values can be found that do not appear on either surface, but we're just honing in on one spot that has values that will not appear on either surface. It's also important to remember that not all the values from this location will work, since we have no idea yet if we're stopping on a column that corresponds to a prime. That was still the part we haven't figured out yet or dealt with. All that remains is to remove any composite values from this location, as well as any non-twin primes, and show that an infinite number of generators still remain. So I do get into doing what I thought I was going to have to do for this, and this will make sense. So this part was a little bit muddied for me to talk through and get through, and you really have to be familiar with it, but trust that what I wrote was right, and you can go back and verify that, rather than just my discussion, if my discussion isn't 100% satisfying right now. But I want to recap a little, and then we'll go on to filtering the general parabola, what we did. So just, if it was confusing, what we did for this last section, I want to go back to where we really felt strong up into that point here. So we realized that we had these two surfaces, and we realized that for a given range of columns and rows, we're looking for certain values that don't appear anywhere on those surfaces to check whether it's prime or not, or in case both of them, whether we have twin primes or not. And instead of going through and saying, we're going to do that anyway in a sense here in a minute, but instead of going through and saying, well, what range and what values and can we find a number, and we're checking all the rows and all the columns, we said, hey, what if we can just find values that never exist? Can we work with those and somehow backtrack and say what our primes or twin primes were? If we can just find an infinite set of values that never exist, then that would be good to go from there. We took this diagonalization property and we used, for example, 49 and 64 here, and we said, hey, look, notice that because of the formulas for these surfaces, that if we go above values in the next column above the diagonal of the previous column will never exist in any of those columns. it's a quick way to rule out a bunch of values that don't appear. And we said that this was the same, but it's +8 for this surface. So we found these trailing values, which are the values in one column above the values of the previous column's diagonal. And those kind of trailing values at the bottom of any column are what we were working with. But because these surfaces we did a substitution of 4-to-1, our value that we were doing in 4 times of it, we then said, okay, well, that gives a range of 8 values for these surfaces. But if we go back to our original thing that we were checking, there's really only 2 trailing values that we have to look at. So that's what we did. And then we got to this part with the parabolas and these equations here, which start to squeeze in on those 2 trailing values. And we said, we noted that when x was even, we noted that because of this was based off of the diagonals, that either x and y were both even or both odd for us trying to hone in on this one value. And we noticed that when x was even, we only get one value in the middle, but when that value itself is composite, it throws everything off. So we said, well, let's just not even deal with that. And let's just look at the values when x and y are odd. When we do that and we don't get something that's an integer of 4, we get these parabolas that are fourths. And they will have 2 values between them. That's what we showed here. But then we said, since they have 2 consecutive values between them, we don't want the even ones again. The even ones are automatically composite and they're going to throw things off. So let's just hone in on the odd values because they have a chance of being prime and not composite. So then we found another parabola which will just select the odd value between our 2 parabolas that we have. The 2 values that we get, we said, okay, this parabola will select our odd value between, and that's kind of where we left off. So that's all we've done there. Again, it takes a lot of steps, so you have to go through and understand it specifically to make sure you don't mess anything up or forget anything. But if you trust that part, or if you learn how to do it, or break this paper down more, or go through again, it's all there. Oops. So that's what we've done, and we still haven't. We're acknowledging. So this x. So whenever we have an odd x, we can have this x squared plus 3/4 generate us a value that will be our odd value between our 2 parabolas. And because there's infinite odd x's, there's infinite odd numbers, we'll get infinite of these values that would correspond to the value between our parabola in some case. But the problem that we were still working with is it's important to remember that not all the values, and I'm just reiterating now, this is where we left off. We don't know if all of these will work yet, since we have no idea if we're stopping on a column that corresponds to a prime. This whole thing was based off this idea that we're looking for these trailing columns and trailing values in columns where that last column corresponded to a prime z in the very beginning. But what we have to do now is we now have to remove any composites from that location that are left. We've got it down to just odds, but we want the odds which aren't composite, i.e. the primes in this location, as well as non-twin primes, and show that an infinite number of these values still exist. So it's this one little, if you think, I said this in one of my other videos, I call values that not exist holes. I call it a hole in the surface in a sense, or a hole in my trailing values. I just tend to use the word hole for a value that does not exist. But, like a hole in the ground, not a whole number, but a hole in the ground. So when you think about the 8 values before we did our scaling by 4, or we did our scaling by 4, however you want to think about it, those 8 values are the 8 trailing values in that column. And when we get it down to our original surfaces, it's just 2 values that would be in that position, that trailing position in that column. And we're saying there's a hole there, that in every so many cases of this, there's going to be an infinite number of values in these positions that never show up on either chart. That's what we're trying to show. And once we get that, we know there's an infinite number of twin primes. And there might be other values that don't show up because we've cut off some edges of different things, and there might be other ways to find values that don't show up, but at least we found one spot where there will never be certain types of values that show up, and thus there's an infinite set of these. We haven't gotten all twins in this case, but we still show that there's an infinite amount of them. We're not finding every instance, just all these ones that meet this requirement in this one area of these charts that we're looking at. There's one area of the surface, or one little value position, if you think about one hole in the surface where the values just won't be there. So how do we do this? Filtering the generating parabola. Okay. So being odd, these values contain only primes and some remaining odd composites. So we said, like, this value here is 7. We've only selected these odd values, so they're, I mean, it's kind of capped and redundant, but they're either odd composites or a prime. So these values contain only primes and remaining odd composites for odd x, because we said this is only for odd x's now is what we're honing in on. The next step is to filter those composites by writing them as the product of two odd numbers. So this is where, and again, I had this first proof years before my second one, a good 4 or 5, or I have to think about it exactly, but a couple years before my second one. And this was part of the thing that led to this last result, which is where it's going to be where I just kind of say, oh, the exercise is left for the reader. And I kind of gloss over it. And it wasn't robust enough. You know, it wasn't rigorous enough. But here you can start, if you watch the first twin prime paper, you can see this is what I ended up realizing was the key to the trick that makes everything easier in the first place. So now this is a kind of a hearkening back to the first paper that I talked about. And we're using, if you want, I'm going to go through this quicker here, but if you want to really understand that logic, go watch the other video on the other paper. I feel it's much stronger than this one. Well, this is right. It's just, it was better. It was better because I had learned stuff over those couple years, and this was one of the key things that I had learned. And that is, primes are odds which are not composite. And that seems kind of obvious. You're like, okay, that's pretty obvious. But that makes a really handy surface to write down to be able to say and talk about these things. Where if you have an odd number that's not an odd composite, you could write that as like a 2a, a 2x plus or 2n plus 1 or whatever variable you want to use is not equal to, in my other paper I said 2a plus 1 times 2b plus 1. You're just saying an odd number is literally not equal to odd composite, which is two odd numbers times each other. So here, this is why you see these two odd numbers times each other. And you get, so odd number times an odd number is this surface. And that represents all odd composites. Same way our original surface in this one was xy, which represents all composites. This surface represents just all your odd composites, if you want to think about it that way. So here we kind of use the trick that we were using from the first video anyway, or something very similar to it. And here we're saying we want this parabola, the values that it outputs, and again, when x is odd, we want these, we know they're going to be odd numbers. In this case, we already showed that with what kind of values and how we're choosing. It's always going to choose just this odd number between our parabolas. But we want it to be prime. We want this value to be prime. And so we don't want this parabola, this x squared plus 3 over 4 parabola, our selector parabola. We don't want it to equal an odd composite. This number here, this represents odd composites. Which leads to the condition that, so when you solve for x here, you get this condition on x. X cannot equal the square root of 16nm plus 8n plus 8m plus 1. So removing those values as input for x leaves only primes as our output. So if you only choose x that are not equal, that meet this requirement, x that are not a form of this, then you'll get only primes as the output. Okay. Because we already said it was odd. Yeah, I'm just double checking for myself as I say it out loud. So we already know that it's odd and that it equals our number in between our thing. And so then, yeah, so when x is not equal this, the output that parabola then generates will be prime. The final step is to filter the regular primes from the twins. If a prime is an upper twin prime, then 2 less will also be prime. We know that. It's been our, how we built this. However, if it's not a twin, then 2 less will be an odd composite. That is, and here's our parabola value, -2, and not equal to, same idea here. We just change the variables because they have to be separate. Which gives the condition that x is not equal to this either. So, therefore, and here's where it starts to drive home, and so here's where I ended in the other video. So we're almost at the end, and I've got a half an hour to explain this, but this is almost at the end, and where we're going to get our equivalence for the twin prime conjecture, if not prove it, or I glossed over it here, or you'd have to go back and do the row analysis that I do in the first paper, or the other paper, I should say. But what are we saying here now? So we get this condition that x can't be this to make the one surface. When x isn't this, the one surface will be prime. And when x isn't this, the other one will be prime. Therefore, when x takes an odd value for which there are no natural solutions to those two equations, 23 and 25, this one and this one, which I just copied down here in general terms with both. Here I said P and Q because technically I wanted you to realize that there are different P's and Q's in these N and M's. But just of that form, So when x is an odd value from which there's no solutions to those equations, then that x squared plus 3 over 4 selecting parabola will generate a value that it's prime, which is an interesting thing just on a side note itself. When I first developed this, I said, oh, that's kind of interesting. You can generate, people are looking for ways to generate primes. So I'll leave it as an exercise to the reader to prove or show, or if you actually went through this whole paper and did the steps that I said and really understood what was going on here, you could prove it pretty easily. But I'll leave it for you to show or at least understand this. Whenever x is not of this form, so if you find some x that is not of this form or of this form, and you plug it into x squared plus 3 over 4, you'll get a prime. So any x that's not of either of those forms plugged into here will generate you infinite primes. And that's kind of interesting on its own. Now, it doesn't give you every prime. Of course, it skips a bunch, but there's a way to generate primes there. Just find any x. And this is, again, same for that. It's much more easier to go to my first paper and you realize what's going on here with the odds that aren't odd composites. And you just pick any number that's not on that surface and you can generate a prime by doing the odd version of that, 2 times that plus 1. And you can generate all your primes that way. But here we ended up extracting out some subset of that, if you will. And it turns out, though, that this is still a true statement. If you pick an x that's not of this form 23 or form 25, and you plug it into here, you will generate a prime number, which is interesting. But that prime number does not appear on either surface. And that's because it ends up in that hole in the trailing locations on the columns, and there's only so much number there. There's only 2 numbers there. We've excluded the even ones. We're just looking for these odd ones, and only certain odd ones that happen to be prime. But when you get a prime in that position, it won't be on either of those charts, is what we've shown. And because it's greater than all the numbers in the columns before it, and so forth and so on. And those numbers will never be on either chart and there's an infinite number of them, because you can just keep plugging them into x squared plus 3 over 4. And so all those primes show up as not on either of those two charts. But we said if there was an infinite number of values that are not on either of those two charts, then there's an infinite number of twin primes. So that's how this proof works. That's what proves it. But here's the part that I was not rigorous at the beginning and just left over for an exercise to the reader or whatever. I said, because it does not appear on either surface, both square roots. So here I'm explaining it a little bit more. Because it does not appear on either surface, both square roots will not be whole numbers, and the original value being checked and 2 less than it will both be prime. Therefore, since there's an infinite number of odd numbers with no natural solutions to x equals this and x equals that, then there are infinite generating values that create twin primes. But there's the part I just kind of threw in non-rigorously. I was like, oh, therefore, since there's an infinite number of odd numbers with no natural solution to this and no natural solution to that. And when I originally had this, my mind just looked at these two forms, 16nm, 8n, 8m, and 1, and the same thing in 9. And I thought it was trivial. I said, oh, that's trivial that there's going to be an infinite number of odd numbers that are not of this form. And I think it kind of is, but prove it, right? Like, go ahead and show that there's an infinite number of odd numbers not of this form. And I said this in my first video on the other type of proof. I think somebody more familiar with modular arithmetic or some of these forms would say, oh, I can prove that pretty quickly. So if you've gotten to this point and you find this interesting and you kind of want to complete this proof, this version 100%, I'm claiming that this is an analog to the twin primes, proving that there are an infinite number of odd x, not of the form square root of this or square root of this, proves the twin prime conjecture. Because it will show that there's an infinite number of values that are not on either of those surfaces and thus an infinite number of twin primes. So here's where I said at the beginning of the first video, we're going to at least get you to an equivalence for the twin prime conjecture. And again, intuitively, I think it's kind of obvious that there's an infinite number of odds that are not of this form or this form. But I didn't show it. And how would you show that? Well, again, the only way I would know how to start to showing it is kind of like I did in the first paper, where I break them down by rows and columns. So I would have to break the equation of this surface under a square root and this one down by rows and columns and try to find, some. Again, you're kind of doing the same thing. You're finding infinite values that always show up or never show up or whatever to prove that there's an infinite number of these odd numbers. But this being kind of incomplete or spurious at the end led me to think about proving just that. How would you prove that this is all, that there's an infinite number of odds of this form or this form? And it led me back to this part here, where I realized at the end it was like odds. 2 odds, multiplied represent the odd composites. And you're saying this thing we already knew was odd in our case of where it came from. We want an odd number that's not equal to an odd composite. And I started with that premise for the other paper and showed that for that paper. And so you're basically doing the same thing, but here it's turned into this version of it. And so, and again, this was a rewrite when I put these two proofs in one paper just to have it all collected and everything. And I had the second proof years later. And I said at this point, the proof concluded in a bit of hurry. And one might notice or still be left wondering a few things about the last few sections. Primarily, and this is things that we'll get into here. What happened to worrying about whether a specific column represented the minimum range for a prime? I kind of stopped talking about that. And I said, well, why does that not matter anymore? And it doesn't. And when you go through and do all this logic, you can see why. But I wasn't very explicit about it in my original proof. And how do we know the value generated won't be on either surface within a domain field? And what about the 2 square roots at the end not being a basis for the odds? I didn't really prove that. And so I talk about that more here, just the kind of way that I am now. I said quasi-circular logic, trivial basis for the odds, and the inspiration for the first proof. That's kind of what I just explained to you. But I do go into a little bit more here, so let's finish with this. We've got another 20 minutes if I want to keep it under an hour. I only think this is going to take another 5 or 10 to finish up. So what's really happening with this proof when understood as a whole? Can it really serve to prove infinite twins? And what about the questions at the end of this previous section? This stuff I just kind of glossed over there. A key to this is understanding how the surfaces in equation 18 are being used and how it relates to the original number being checked. The surfaces are used such that one is checking to see if the number being queried appears on the surfaces within a field. If it does, then the number is prime. In the case of those primes, this means that the prime does not appear on the field. So when the process is reversed, that is looking for values not on the field to generate primes, it turns out one is looking for primes not on the field, which is what it's circular logic there a bit, but that's what we got at the end, where we're still kind of looking for primes that aren't on the field. That last thing we said is a odd that's not composite, and we ended up looking for primes that weren't on this other field that we had generated, not necessarily the same field or whatever, but that is, in case of the primes, it means that primes did not appear on the field. So when the process is reversed, that it is looking for values that not on the field to generate primes. It turns out that one's looking for primes not on the field. Okay, this is why it's referred to as quasi-circular logic. It's not that one actually has to know the primes to find the primes, even though it's kind of like built in. You're doing this prime check, if you would, but rather that if the number happens to be prime, then it won't appear on a specific field of the surface, i.e. that little trailing location, which in turn then means the square root won't be whole, which in turn means the number is prime. Okay, it just happens to be how that works in this case. No, it doesn't mean that primes don't appear on those surfaces either. If you look at the values on those surfaces, primes do appear on some of those surfaces. They do, just not in the domains that would make them not prime. So this goes back to that other domain and range thing, which I hadn't quite talked about or finished talking about, and why it mattered. And again, the quick reason of why it doesn't matter. Well, I guess I shouldn't say that because I'm just going to muddle things worse. But let's see, because I know I talk about it more here in a second. But it basically is because you're just looking for numbers on that surface that don't exist in a proper location, and that's the caveat. And me doing this, I had worked out all these rows and columns and knew which locations were allowed and which weren't. But okay, let's go into a little bit more here. We also know that there are infinite primes generating infinite values, i.e. the primes themselves not appearing in specific fields. Since each number being checked only corresponds to one domain field. So yeah, this has to go back into that domain field, like how do the primes or the numbers you're checking correspond to the domain field. When a prime is found to not appear in a trailing location, it means that column is the maximum of a domain. So it had to correspond to when these were the maximum of domains, since it can't be found in a lesser row or column. Okay, here, hold on. Since each number being checked only corresponds on one domain field. So now we're kind of reverse engineering what we did at the end. And we said, we could just, because at one point, if you remember in the first video, I said, oh, well, let's just assume it for any column, because we know for some column that corresponds to some domain for certain numbers that you would be checking in a range of those numbers or something. So when a prime is found to not appear in a trailing location of the column, it means that column is the maximum of a domain, since it can't be found in any lesser row and column. This is true for, and I show where it's true, x squared is greater than this square root 8. Or in other words, when x is greater than or equal to 5. Again, there's the first few cases in the chart that rule does not follow just because you're dealing with like low numbers or the first few primes. So this is valid for any x greater than or equal to 5. Which again, I used that other requirement at one point that said it's only valid for x greater than or equal to 24 or wherever it was. But that's fine, because you can rule out the first 24 columns of the chart, and everything after that is, you still have infinite values after that where this system works. Again, there are other primes that are confirmed by not being found in their corresponding fields in a portion of that field other than the trailing locations, but those aren't used in this case. So it's just other stuff that we ignored. This is why worrying about a column being a maximum range is not a concern, since by demanding that the value found in the trailing location to be prime 22, it's ensured that it is. So again, it's been years since I'd look at this, and I'd have to go back and refamiliarize myself with it 100% a little bit more to really explain it to you in a way that would make you feel confident about it or drive it home. But here in words is the logic that I realized there's a reason that you can, again, this row thing ends up, this column thing ends up not mattering because in all the frivolous cases or the extraneous cases, you can just kind of rule them out because you're tightening your bounds, you're not loosening them. You're making the criteria harder and giving yourself less locations to find these infinite holes, but you end up finding some anyway in that one spot. And again, it's been years since I looked at this, but that's I'm trying to just paraphrase in the sense of what you're looking to do here and why it works. There are other primes that are confirmed by not being found in their corresponding fields in a portion of that field other than the trailing locations, but those aren't used in this case. So this, I think, was going back to saying that, again, when you do, there are some primes that show up in that chart, but when you do find primes that don't show up in that chart, you always get a prime or a twin prime out of it. And I'm kind of getting it in my head now. I'm remembering it. And for the cases where those primes are somewhere else in the primes that don't show up are somewhere else in the chart other than that trailing location, you're just skipping those. In a sense, yeah, you'll have to go out more columns into more trailing locations to find one that's in that little location, but there's still an infinite number of those, so you're okay. So that column argument ends up just kind of being like trivial. Because you've still had an infinite number of them in this other location is all I was trying to get at here. And if I really had to go back and break all this down and pull out the, and pull out the rows and column stuff and state it or teach it to somebody explicitly, I could. Probably take me a couple days to refamiliarize myself with it. But generally, there was something that I found that you're ruling them out anyway. And so it ended up being a non-issue. These last facts, along with a statement about the basis for the odds, are what lead to the need and desire for better proof. But like I said, you can hear me talking about it. It's not really convincing unless you sit down and work with it and know that what I said here is true. And this was, I think, one of the first proofs I wrote like 12 or 15 years ago before I even knew how to use LaTeX. Or latex, LaTeX. And it's what spurred me to find something more rigorous, which is what I did in the other one. That is, we go all the way through the process just to arrive to those square root equations. At one point, using the reasoned parabola with odd inputs and odd inputs and outputs, and then simply removing all the composites and all the twins by doing that process twice by having it not equal to that composite surface. We've basically checked for twin primality right there, only to say that those numbers mean that the square roots aren't whole and thus create twin primes. It's okay because we needed to, and I did this to find and prove an infinite generator, but it seems redundant. So that's when I realized that the material at the very end of this proof was the basis for what I really should have been starting with in some form for the other proof, which is the other videos I have up. And it also relies on those statements that do not remove so many odds, such as there's an only infinite number of odds remaining. That part where I said, I just kind of said, okay, these two square roots, sure, there's an infinite number of odds that are not of this form. And it seemed trivial, but that's not good enough. While a plot of those surfaces or a table seems sparsely populated, they don't remove too many odd numbers. It's better to show it explicitly. It was sometime later and from all those understandings that I realized why not just start directly from there with all the odd numbers and remove all the composites. I also realized that some surfaces are easier than others to show that they're not a basis for certain sets, i.e. that all the work I did in the other proof with the rows and showing that there's an infinite set of integers left over that always create values for any and all in every row, that they don't, they're not a basis for that set of numbers. So this is what eventually led to the second proof presented in the first half of this paper, which is the one that I put up videos for first on the channel. So again, when I said at the beginning of the first video for this set here, for this proof, it might not have been quite as satisfying, and it's something that you really have to familiarize yourself with it if you're going to feel confident about it. But if you do take the time to go through everything that I wrote here and develop the topic and start to understand what I did, and could I eventually make this a little bit more rigorous and explain it better in words if I really took time and months and stuff? Sure, maybe somebody can come through and say it a little faster than I can. Or what you do get out of this version, though, is you get this neat equivalence for the twin primes that technically you could just start from here and say, proving that there's an infinite number of odd numbers not of this form or this form proves that there's an infinite number of twins. Because when you prove that, they fit into this generator function in such a way that all those values won't be on both the surfaces, because certain numbers won't be whole under the square root, which will make things that don't exist whole later, which means there's numbers that aren't on the surface, that kind of thing. So it's still here for people who are just really into this kind of topic, and because it's what led to the other one, and I felt like making a video, and I had an hour or two today to sit here and do this, just to create some more content. But its conclusion is showing that using an odd x, which was properly filtered for that x squared plus 3, so odd x that aren't of those two square root forms, plugging it into here will not only give you a prime itself, but then that prime will prove that there's infinite twins, because there's an infinite number of those, and those are numbers that aren't on the surface, or generate numbers that aren't on the surface. And these values always create twin pairs when used as input to the original equations. It should follow that one could replace the z minus 2 with z minus 2n and show that the method can be used for any even-sized prime gap. Right, because the twin prime conjecture says, are there infinite number of twins? But the greater twin prime conjecture, or the even gap prime conjecture, says, are there infinite primes of any size even gap? You could use that same process here, or the same process I do in the other paper. And then I just summary the main paper, which I had actually shown in the other videos, two different methods to show there's infinite many twin pairs. So I guess I'm going to leave it at that, since we're at 53 minutes. And yeah, it's a lot to take in, and you really have to familiarize yourself with what's going on. But this would be enough for somebody who's really interested to repeat these steps and go through it and become familiar and say, what did he mean here? Oh, how did he do this? Where did that value for the ranges come from? Double check it all. And once you become familiar with it and what you're trying to do, plot out some of those charts and get familiar with which sections of the chart you're looking at and this and that. You'll see that it's viable. It's viable as long as, again, it's viable as long as these two, there's an infinite number of odds, not of this form or of this form here. Right? That's what it really hinges on. And so I guess I'll leave it at that. Here's your equivalence for the twin prime conjecture. And if you have any questions, feel free to leave them in the comments. I hope you enjoy this for the people who are into this kind of topic. And I don't know that I have too much math I'll put up on the channel at this point. I put up my prime paper with the how to make primes and composites and prime factors and stuff. I put up my Riemann paper. I put up now the twins and the stuff material I had on the twins. I don't have too much more. I haven't really worked on it. I could use this technique for like Mersenne primes and Sophie Germain primes or Goldbach's conjecture and other stuff. And I ranked them at one point. Some are harder than others. This does not work as well for Goldbach or I think Mersenne, but I think it does work real well for it ends up working for the Sophie Germain. And I think of that one I almost could just write out in the similar proof as like the first version of this, where you actually do the rows and columns method. But I haven't done that, and I've got other things to worry about in my life right now at the moment. I have one other paper that was just a totally different paper on this other technique that I developed, which has to do with piecewise functions and how you can turn piecewise functions into kind of continuous or non-piecewise functions and things that you can do with them. And during that paper, I also just found a couple other interesting formulas that have to do with step functions and approximations for step functions and things like that. Rapidly converging functions that have to do with using them to substitute. So I might eventually, probably in the next week or two, if I'm still making these, I might put that paper up and discuss that. It's just its own topic. It's not like a famous unsolved problem or something. And the other material I have would probably be back to the circle. If you watch the channel, you'll see there's some math videos, but you'll also see that there's some circles and some game videos. So I might talk more about the game next. But anyway, I'll leave it here. You guys have a great day, and thank you for watching.